Hey everyone, I'm Muifaden and welcome to the final video in our Solid Principles series. Today we're tackling a big one, the Dependency Inversion Principle or DIP. Now I'll be honest, this one sounds scary at first, but hang in there, I promise it's not that complicated. In fact, this principle is the secret sauce behind flexible, scalable, and testable software. If you've ever found yourself stuck with tight tangled code that's hard to change, DIP is your new best friend. By the end of this video, you'll not only understand what the dependency inversion principle is, you'll also see how it can make your code cleaner, smarter, and way easier to manage. Let's wrap up this series strong and dive into the final solid principle. Here's the official definition of the dependency inversion principle. High-level modules should not depend on low-level modules. Both should depend on abstraction. Sounds kind of philosophical, doesn't it? Okay, let me break that down in normal language. Think of your code like a business. The high-level module is like your manager. It handles the strategy and big picture. The low-level module is like your intern. It handles the small details. Now, normally the manager tells the intern exactly what to do. But what if the intern changes or their job changes? Suddenly, the manager has to adjust everything. That's chaos. DIP flips this around. Instead of having the manager rely directly on the intern, both of them follow the same job description, also known as an abstraction. That way, the manager doesn't care who is doing the job, as long as they follow the rules in the interface. This makes your code flexible, plug and play, and easy to update. Let me show you why this matters with a few quick points. So, why does the dependency inversion principle matter? First, it makes your code way easier to change and extend. When your high-level logic doesn't depend on the nitty-gritty details, you can swap things out, upgrade parts, or add new features without rewriting your entire app. Next, it decouples high-level and low-level logic. That means your core business logic isn't tied to any specific implementation. Your code becomes more modular and less fragile. And finally, it makes your code easier to test and scale. You can plug in mock objects, fake services, or different data sources without touching your main logic. That's a huge win for anyone working on larger systems or building for the long run. Let's look at a real-world example to understand the dependency inversion principle. Here we've got three vehicles, a car, a truck, and a bus. Each one drives a little differently, right? Different sizes, different handling, different controls. Now imagine being this driver. He's trying to drive all three vehicles, but they each have their own weird dashboard, pedals, maybe even different steering controls. And he's like, wait, how do I even start this thing? That's what happens when your high-level logic depends directly on different low-level details. So instead of having the driver deal with each vehicle's unique control, we introduce a standard interface, something like a simple steering wheel and pedals. Now, it doesn't matter which vehicle he drives, car, truck, or bus. They all connect through this same control system. And just like that, our driver is no longer confused. He's happy, confident, and in control. Because now he's depending on one clean interface, not three different systems. This is exactly what dependency inversion is all about. Your high-level code, the driver, shouldn't depend on the details of each vehicle. Instead, both should depend on the abstraction, the common interface. It makes everything simpler, cleaner, and easier to swap out later. Let's take a look at what happens when we don't follow the dependency inversion principle. Here we've got two classes. First, backend service. It fetches data from a database. Second, report generator. It creates reports using that data. So, what's the problem? Well, report generator directly creates and uses backend service. It tightly coupled to that specific implementation. Now imagine later on you want to change the data source, add caching, switch to an API instead of database. And guess what? You have to go into report generator and change things there too. That means more work, more bugs, and way less flexibility. This kind of design breaks the dependency inversion principle because the high-level module, report generator, is directly depending on a low-level module, backend service, instead of relying on an abstraction. Alright, now let's do it the right way, using the dependency inversion principle. We start by creating an interface called data source. This is our abstraction. It defines what our data provider should do, in this case, just fetch data. Then we have backend service, which now implements that interface. It still connects to the database, nothing has changed there, but the real magic happens in report generator. Instead of creating the backend service directly, we pass in any object that follows the data source interface. So now report generator doesn't care where the data comes from. It just knows how to call fetch data, and that's the dependency inversion principle in action. We inverted the dependency. Now both the high-level and low-level modules depend on an abstraction. That makes our code easier to change, easier to test, and much easier to maintain. Let's wrap it up with the key benefits of using the dependency inversion principle. First, it makes your code flexible and future-proof. You can update or replace parts of your system without breaking everything else. Second, it lets you swap components easily. Want to use a different backend, a mock data provider, a faster database? No problem. As long as it follows the interface, your main logic doesn't need to change. And finally, it makes testing way easier. You can inject fake or test versions of your data source without touching your real logic. No hacks, no rewrites, just clean testable code. And that's a wrap on the dependency inversion principle. The final and possibly the most powerful principle in the solid design lineup. We've seen how depending on abstraction instead of details can make your code flexible, testable, and so much easier to evolve over time. And just like that, you've made it through the entire Solid Principle series. Let's do a quick recap. S. Single responsibility. One reason to change. O. Open closed. Extend without modifying. L. Liskov substitution. Subclasses should work like their parents. I. Interface segregation. Only depend on what you need. And finally, D. Dependency inversion. High-level code shouldn't care about low-level details. Pretty solid, right? I've shared the Python and Kotlin code examples on GitHub. The link is in the description below if you want to check them out. If you enjoyed this series or learned something new, go ahead and like the video, subscribe to the channel, and drop a comment. I'd love to hear what you think or what you'd like to learn next. We've got some awesome content coming up, especially if you're curious about AI, software architecture, or building better apps. Thanks for joining me through this journey, and I'll see you in the next video.